Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Glad to be here.
Today, we are ripping the cover off one of the most foundational and I think one of the most fascinating components in the physical world, the gear.
Absolutely. It's everywhere.
And for this deep dive, we are going way beyond just, a simple diagram of two cogs meshing.
Oh, yeah.
We are scrutinizing the stack of sources you provided, and these are highly technical papers on everything from advanced geometry to metallurgy, manufacturing, for really high-performance applications.
They are. From an F1 gearbox to a massive industrial crane.
So this source stack is incredibly dense.
It is. We're talking fundamental geometry, material specs from the American Gear Manufacturers Association, AGMA, and then some really specialized research on failure modes, ISO standards.
The ISO 6336 suite.
That's the one. So our mission today is really to distill all of that, that heavy engineering work into clear, actionable knowledge.
A shortcut to understanding what makes a world-class gear set actually work. Okay, so let's start right at the foundation, because even the core terms can be a little confusing.
They really can.
When you have two gears in mesh, what are the official designations? We can't just call them the big one and the small one, right?
Definitely not. No, the smaller the two gears, and this is regardless of whether it's driving or being driven, is always called the pinion. The larger one is simply the gear.
And that distinction is important.
It's critical. They often have totally different design requirements, different failure modes.
And the main function, the speed change, that's just the ratio.
Right. And that's just simple arithmetic. You divide the number of teeth on the gear by the number of teeth on the pinion. That's the basis for everything.
It's amazing how these complex systems really just boil down to a simple count. Now, let's get into the anatomy. We need to define tooth size. For engineers working in the imperial system, we rely on the pitch diameter, but how is that standardized?
So in the imperial system, tooth size is measured by the diametral pitch, or DP. And you should think of it fundamentally as a measure of density.
Density. And what does that mean physically? What does diametral pitch represent?
It's the number of teeth on a gear divided by its pitch diameter. So essentially it tells you how many teeth can fit into 1 inch of that diameter.
So a larger DP number means smaller teeth.
Exactly. The larger the value, and it can range from, say, 1/2 all the way up to 200, the smaller and finer the teeth themselves are.
Okay, so that's the standard for imperial. How do metric designers handle this? Is it a totally different philosophy?
It's an inverse relationship, but I think it's a much cleaner measurement. It's called the module.
The module.
And the module is simply the pitch diameter in millimeters divided by the number of teeth. It represents the actual size of the tooth.
Ah, so it's more intuitive.
Way more intuitive. A larger module number means a larger, beefier tooth. It's that simple. And these can range from, 0.2 up to 50.
So that's what determines if a gear is microscopic or, massive.
Precisely.
All right, let's break down the individual tooth profile, that vertical geography, the addendum and the dedendum.
Right. So the addendum is the radial height of the tooth above the pitch circle. For a standard tooth, that addendum equals 1.000 divided by the diametral pitch.
Okay, and the dedendum?
The dedendum is the height below the pitch circle.
Yeah.
And that value is always slightly larger to ensure there's clearance. It's a 1.250 divided by the diametral pitch.
And that extra clearance is just to stop the tip of one gear from crashing into the root of the mating gear.
That's it. It's critical for preventing interference.
That math sets the standard, but this is where it gets interesting. When designers start actively modifying that profile, you hear about long addendum design.
Yeah, that's a really sophisticated adjustment. What they do is they increase the pinion's addendum and then decrease the gear's addendum by the exact same amount.
Right.
And this isn't arbitrary.
Right, there's a reason.
It's done specifically to improve the contact ratio and, really importantly, to decrease the chance of harmful undercut on that small pinion. It just makes for a smoother transfer of power.
That attention to detail brings us to maybe the most defining feature of a modern gear, the curve of the tooth itself. I know historically they used cycloidal curves in watches and things.
Right, for fine mechanisms. But today, the involute curve is king.
So why that specific curve? What's the magic?
The involute curve is it's an absolute stroke of genius in mechanical history. Its key advantage is that it ensures continuity of movement. It maintains what's called conjugate action.
A perfect rolling relationship.
The perfect roll for a constant velocity ratio.
Yeah.
But here's where it gets truly fascinating for real-world applications.
Go on.
That perfect action is relatively independent of small errors in the center distance.
So if your gearbox housing flexes a bit under a heavy load or the manufacturing is slightly off.
Exactly. The involute geometry inherently compensates. It maintains that constant, perfect roll. It's what stops a gearbox from binding up.
It's like a built-in failsafe.
In a way, yes.
Okay, finally, let's define that critical angle of contact.
That would be the pressure angle. It's the slope of the gear tooth right at the pitch circle. 20 degrees is the widely accepted industry standard.
Why 20?
It's a great balance between strength and smooth engagement. But the sources show all sorts of values, from 14.5 degrees for super smooth running up to 27 degrees for, pure strength.
Okay, moving from the geometry to the material itself. When you need high load capacity, steel is obviously dominant.
It is. But then you have iron, which is often favored for its castability and its inherent wear resistance in big, slow-moving applications.
And bronze.
Bronze is often specified where friction is a major concern or in non-sparking environments.
Yeah.
And then, of course, you have plastic gears, easy to mold, quiet, but
Very limited load capacity.
very limited, yeah.
So for high-performance steel, the metallurgy and the heat treatment, that's everything. You've got through-hardened steel, which tops out around Rockwell C42.
Right.
But for extreme power density, designers turn to case hardening.
Yes, case hardening, which is usually done through carburizing. It fundamentally changes the gear. It hardens just the outer shell, the working surface, to an extreme level, often hitting Rockwell C60.
But the real insight, and this is what many find kind of paradoxical, is in the core.
Exactly.
Why does leaving the inner core of the gear softer actually make the whole thing stronger?
It's all about toughness and shock absorption. That hard outer shell gives you incredible surface strength and wear resistance where the teeth make contact, but the softer, lower carbon inner core stays ductile.
So it's like a cushion.
It is. When the gear gets hit with an impact load or a big torque spike, that softer core absorbs the shock. It prevents a catastrophic fracture from starting and running right through the tooth.
But even the best material can fail from fatigue. A really common failure mode designers fight is pitting. What's happening there?
Pitting is a classic surface fatigue failure. It happens when the repeated cyclical load on the surface exceeds the material's endurance limit. Fine cracks start just below the surface, they grow, and eventually eject little pieces of material. That's what leaves those small craters.
Can a gear survive that?
Sometimes. You can get what's called initial stage pitting. This happens when there are little high spots on the gear surface. But once those surfaces wear in and the load gets distributed evenly across the face, that pitting can just stop, and the gear is still perfectly functional.
Now, the cutting edge of this analysis is something called tooth flank fracture, or TFF. That sounds a lot worse.
It is. TFF is insidious because the failure doesn't start on the surface. It initiates beneath the active flank, often deep in the material near the tooth root.
Which means the internal stress from manufacturing is a huge factor.
It's decisive. That residual stress can either be your best friend, if it's compressive, or your worst enemy, if it's tensile.
This focus on internal quality leads right back to material cleanliness. I saw that high-performance gears now require a GMA Grade 3 cleanness. What does that mean in practice?
It means we're looking at ultra-clean steel. We're controlling not just the alloys, but the size, the quantity, and the distribution of tiny, non-metallic inclusions in the steel.
Because those are the weak points where cracks start?
They're almost always the initiation sites for fatigue cracks. By minimizing them, you drastically improve the material's fatigue life.
And what's the payoff?
The sources show that by using these high-strength, high-toughness steels, you can get a 30% reduction in the gear set's mass.
Wow.
Or, if you keep the mass the same, you can get a 45% increase in torque capacity. That's a staggering jump in power density.
Let's shift to how these precise shapes are physically made. You can break gear cutting into two main families, generating and forming.
Right. Generating is where the tool's motion, not its shape, creates that involute profile. The most common method here is hobbing.
Hobbing?
It uses a helical, sort of thread-like tool. The tool and the gear blank roll together, and it develops several teeth at once. Very productive for external gears.
And forming.
Forming is the opposite. The tool's pre-existing shape is just imparted onto the workpiece. Think of shaping or milling, where a single cutter carves out the space between the teeth.
Now, manufacturing used to be really dependent on these specialized tools, which meant long lead times. But CNC has changed the game. You mentioned something called generative gear milling or milling.
Exactly. This uses modern multi-axis CNC machines and universal tools like end mills to cut the profile. The huge advantage is that one standard tool can cut almost any gear
Any module, any helix angle.
without needing a dedicated custom hob for every single design. It's a massive win for flexibility, especially in prototyping.
What about internal gears, the ring gears in planetary systems?
Historically, those were slow to make. But now, a process called skeeving is getting a lot of attention, mainly because of recent progress in NC technology.
Okay.
Skeeving uses a cutter that operates at a really high speed ratio to the gear blank. It promises huge improvements in productivity and flexibility for making internal gears.
So once the gear is cut and heat treated, you have to finish it. Why spend the extra time and money on grinding or honing?
It's non-negotiable. Heat treatment gives you the strength, but it always introduces distortion. Always. And that distortion kills your accuracy and your surface finish.
Which you need for load distribution and, I assume, for noise?
Absolutely, for NVH performance. So finishing operations like grinding restore that precision. You can do it with high productivity threaded grinding wheels, which are basically big abrasive hobs, or with single rib wheels for more complex shapes like worms.
So even a perfectly manufactured gear still needs these tiny adjustments, these microgeometry modifications, to run well in the real world. Why build planned imperfections into a precise part?
Because in the real world, nothing is perfectly rigid. Under load, shafts flex, bearings shift, housings move.
Right.
These modifications ensure that the load stays distributed properly across the tooth face. If you don't modify the geometry, the gear won't work as designed once you apply torque.
So this brings us to the first one, crowning and end relief. Is this basically building an optical illusion into the tooth, so when the shaft flexes, the contact is still perfect?
That's a perfect analogy. Crowning makes the tooth face slightly convex along its length. So when the system deflects, instead of the load slamming onto a sharp edge, the crown keeps the load distributed near the center. It builds forgiveness into the gear.
And the second modification is even more subtle. Profile modification. This is where you make the involute profile intentionally incorrect.
Right. This is what I'd call anticipatory engineering. The profile is modified so that the tooth is intentionally wrong when it's unloaded.
So that when the full operational load hits...
and the tooth flexes or vaults under that pressure, it deflects into the mathematically perfect involute curve.
You're using the material's own elastic deformation to achieve perfection under load. And this is key for reducing NVH noise, vibration, and harshness.
It is the primary tool for reducing NVH. Any sudden jolt during meshing creates noise, and this planned distortion eliminates that jolt, ensuring a smooth entry and exit.
And this is where it gets really cutting edge. Asymmetric gears. The sources suggest a 30% increase in power capacity. How is that possible?
So in a traditional gear, the tooth profile is identical on the drive side and the coast side. An asymmetric gear uses different pressure angles, different thicknesses on each side.
Why?
The insight is, if your gear set only transmits high torque in one direction, like a car's final drive, you can put all the design strength onto that driving flank, make it much, much stronger.
And this optimization can really boost power capacity that much.
Up to 30%, yes. The challenge, though, is that our current calculation standards, like ISO, have to be adapted to accurately predict the stress in these new designs.
Finally, we have to talk about backlash. The clearance between mating teeth. Why do we need clearance if we want precision?
You need it for a lubricant film, and most critically, for thermal expansion. If you had zero backlash, the gears would bind up the second they got warm.
And this is a bigger deal for plastic gears, I take it.
A much bigger deal. Plastic gears need a lot more backlash because they have a much higher rate of thermal expansion than steel, and they also swell when they absorb moisture.
So how do you get rid of backlash when you need extreme precision, like in a machine tool?
For that, you use specialized designs, like a duplex lead worm gear. This system has a different pitch on the right and left tooth surfaces of the worm.
Okay.
By shifting the worm axially, you can precisely adjust and minimize the backlash. It gives you a tuning mechanism for ultimate precision.
All of this complex design has to be backed up by rigorous standards from bodies like AGMA and ISO.
Absolutely. The ISO 6336 suite, for instance, sets the global guidelines for calculating pitting resistance and bending strength. To assess bending strength, the risk of the tooth snapping off designers use metrics like the geometry factor for bending strength. The J factor.
The J factor.
The J factor synthesizes all the geometric properties of the tooth root, the curvature, the pressure angle, to accurately predict the stress right where it matters most. It's one of the most critical factors for predicting tooth survival.
But modern engineering isn't just about static formulas. We're in a world of advanced digital modeling.
We are. The digital backbone relies on two main methods: loaded tooth contact analysis, or LTCA, and the finite element method, FEM.
What does LTCA do?
It simulates exactly how the load is distributed across the tooth, face, and flank when the gear set is actually operating under real-world conditions. This lets you verify your flank modifications before you ever cut steel.
And FEM takes that even deeper.
To a full structural analysis, yeah.
And for validation, physical testing is still key. I saw a mention of a very specialized test.
The single-tooth reversible bending fatigue test, or STRBF.
Right.
This lets engineers test teeth under fully reversed loading, where the load ratio is R equals -1.0. This is a critical scenario for idler gears or planet gears in an epicyclic system, which transmit power in both directions.
And this brings us full circle back to the real world. We're seeing the rise of smart gearbox technology. This moves maintenance from being reactive to predictive.
Precisely. This is the proactive future. High-end equipment now uploads telematic data load cycles, temperatures, speeds from the operating gearbox.
And that data gets fed back into the same simulation models used in the design phase.
Exactly. It converts that operational data into real-time reliability predictions. The system can then send a recommendation, maintain, or replace directly to the operator. It's about preventing failure, not just reacting to it.
So we've taken this incredible journey. It's clear that a high-performance gear is no accident. It's this calculated blend of material science, advanced manufacturing, microgeometry, and digital analysis.
And what's fascinating is how it all comes back to this core tension in modern design: the constant struggle for both high load capacity and low noise excitation.
And those two goals often fight each other.
They absolutely do. They demand incredibly precise analysis and carefully negotiated trade-offs right at the beginning of the design stage.
So if we connect this to the bigger picture, knowing that the strength of these grade 3 steels is tied directly to reducing microscopic inclusions, we see that gear design is shifting. It's no longer just about the strength of the part, but about optimizing based on micropurity.
Yes. Okay.
So does the push for ever cleaner steel eventually become a limiting factor? What happens when we finally hit that ceiling of material purity, forcing designers to find all future gains through geometry alone, like with those asymmetric profiles? Something to mull over next time you hear a high-revving gearbox whir.